Hello, I am Sambit Giri. I am a fellow at the Nordic Institute for Theoretical Physics, or NORDITA. I will discuss the prospect of detecting beyond standard model cosmology through the observation of the epoch of reionization. The work I will present now was carried out in collaboration with amazing researchers is listed here. I want to begin by giving a broad overview using this illustrative image of the standard cosmological model of our universe. At the beginning, the universe was in a hot and dense state, where the matter and photons remained coupled to each other. At a certain epoch, the universe became cold enough for photons to decouple from matter and become free streaming. We see these photons as the cosmic microwave background radiation. After this time, the universe remained dark for a very long time, which is known as the Dark Ages. This Dark Ages ended when the first stars and galaxies formed in our universe. This is a landmark event as the first galaxies emitted energetic photons that ionized the gas between them, changing the conditions for further galaxy formation. In the second panel here, I show an ionization map of the intergalactic gas evolving over time from left to right. The light blue regions show the ionized bubbles formed around these first sources. This process of formation and evolution of ionized bubbles around the first light sources is known as cosmic reionization. As the first galaxies cause the ionization, they reside inside these light blue ionized bubbles. These galaxies are being currently observed by the JWST. The most important ingredient for formation of structures in our universe is the dark matter, which constitutes most of the matter in our universe. Here, I show the contribution from different energy present in our universe, which is taken from the latest Planck observations. Now, I show you a snapshot from an N-body simulation where the dark matter particles are cold and slow moving. These dark matter interacted due to gravity and created gravitationally bound structures known as halos. Ordinary matter fell into these halos, leading to formation of stars and galaxies. Therefore, the properties of these galaxies, such as their number and distribution, would depend on the nature of this dark matter. Though the cold dark matter model has proved to successfully explain most of the cosmological observations, they have problems at small scale, such as the missing satellite problem and the cusp core problem. Therefore, several dark matter models were theorized, such as the warm dark matter model. In the right panel, I show a snapshot from our N-body simulation, assuming the dark matter particles to be warm and fast moving, which have a mass of 0.5 keV. The fast, warm dark matter particles will remove small scale structures. Just to guide the eye, let's focus on only the green squares in both these panels. There are less number of overdense regions in the right hand panel compared to the cold dark matter scenario, which is shown in the left panel. These bright overdense regions represent the locations of halos in both these scenarios. We could also have scenarios where the dark matter is a mixture of cold and warm particles, such as the middle panel here, where we assume 50% of each of these two type of particles. The overdense structures in this mixed dark matter case is somewhere in between the two extreme scenarios of completely cold and completely warm particles. To make this comparison more quantitative, let us look at the matter power spectrum. They show the strength of spatial fluctuations of matter distribution at different scales. Here in this plot, the left represents large scales while the right represents small scales. For the non-standard dark matter scenarios, the fluctuations are suppressed at small scales as compared to the cold dark matter case. The suppression is stronger when the model consists of more warm dark matter particles. Therefore, the suppression strength is more for 100% uh, warm dark matter particle compared to the mixed one where there is just 50% particles which is warm. The scale of suppression is decided by the mass of the warm dark matter particles. Here in the right panel, I show warm dark matter scenarios where they are completely warm but with different masses. Less the mass, larger is the scale below which fluctuations are removed. Let us now look at the impact of this suppression of scales on the dark matter halo properties. Here I show the number density of halos as a function of their masses or the halo mass function. Clearly the, clearly the number of small mass halos are reduced in the non-cold dark matter scenarios. If we look at these halo mass functions at a higher redshift, here I show you redshift 6, the differences are more visible. As cosmic reionization occurs at these high redshifts, we expect their observations to have more constraining power. Let me now go back to a simple picture of cosmic reionization. Until the formation of first stars and galaxies, the universe predominantly remained neutral. Here, the blue background represents this neutral gas. The ionizing photons emitted by these sources ionize the gas around them, forming these ionized white ionized bubbles. We have started to observe these light sources with the JWST. Therefore, we want to know if we can already say something about the dark matter using these observations. We took the currently available observations from JWST to test their sensitivity to study dark matter models. Here I show all the redshifts at which we compared our models. But let me focus on one of these redshifts only. Here, redshift 6. This plot shows the number density of stars as a function of their masses. All these scatter points represent the JWST data, and the lines represent our models. The different colors of lines show different dark matter scenarios. They are listed in the right here. For the thick lines, we assume that all the ordinary matter that fell into the dark matter halos were converted into stars. This gives a physical upper limit on the stellar mass function. The thin lines represent our parameterized galaxy formation model, where we fix these parameters using data points where the explored dark matter models do not show any difference. Here it is roughly about 10 to the power 9 solar mass halos. For a model to be allowed, the thin lines must lie somewhere inside the data point and their corresponding thick line. In this first order comparison, we find that the 1.5 keV warm dark matter model is ruled out. However, we leave a proper statistical analysis to the future when the data will become more robust from these observations. Another method to observe the epoch of reionization is observing the neutral gas around the galaxies using the 21 centimeter signal. This is a signal produced by the spin flip transition in the ground state of neutral hydrogen. Observing this signal over several redshifts will help us understand the impact of these first light sources on their surroundings. This signal can be observed by radio telescopes such as SKA and the EdgeS experiment. The 21 centimeter signal is observed at different as the differential brightness temperature by the radio telescopes. The sky average 21 centimeter signal or the global signal will be observed by single antenna experiments such as the edges. Here in the right, I show you the equation for the differential brightness temperature, and this differential brightness temperature depends on the neutral fraction of the gas and also the gas temperature. And these two quantities are affected by the photons emitted by the first light sources. In the left panel here, I show you the redshift evolution of the global signal for the three different dark matter scenarios, namely the cold dark matter, mixed dark matter, and warm dark matter. And we have assumed the same source properties for these three cases. So there is clear differences in the signal, which can be used to distinguish between these dark matter models. The interferometry-based radio telescopes such as LOFAR, HERA, MWA, and upcoming SKA will observe the fluctuations in the distribution of the signal. We have developed a new halo model-based framework to model this spatial distribution. In this toy example, I want to paint a naive picture of the halo model approach. We assume that the distribution of the signal follows the distribution of dark matter halos. This is a fair assumption as the light sources reside inside these halos, shown here with the star symbol. And the change in the signal happens around these sources. Here, the influence of each sources is shown with the colored circles. As the ionized bubbles will grow and overlap over time, we have to carefully account for these overlaps. I will not go into the detailed treatment uh, method in this talk. Please check the references in the bottom right corner for the detail. I just want to mention that the power spectrum is defined by two terms, namely the one halo term and the two halo term that are pictorially shown in the left and right panel respectively. The one halo term gives the correlations between the points inside the sphere of influence of the same dark matter halo, whereas two halo term gives the correlation of points in two different spheres. This calculation gives a very fast method to model the 21 centimeter power spectrum. We can easily extend this framework to higher order statistics, such as the bispectrum and trispectrum. Using this framework, we studied the 21 centimeter power spectrum. We see similar differences in the power spectrum for the three dark matter models. The right panel shows the redshift evolution of the power spectrum at a wave number of 0.1 h/over megaparsec, which is being observed by several radio telescopes currently. To understand the constraining power of future observations, we performed a forecast study assuming the true universe to be made up of cold dark matter. Here I show the expected power spectra observation with upcoming SK telescope. The shaded region gives the error estimated assuming a 1,000-hour observation with SK. As the differences in the dark matter models occur at the small mass end, we assumed three different star formation models. The bottom right panel shows these three models. The DPL model stands for double power law that explains quite well the available ultraviolet luminosity function observations. The truncated model represents scenarios where star formation is inefficient below a halo mass of 10 to the power 8 solar masses. Whereas in the floor model, the star formation is assumed to be very efficient at this small mass end. We conducted a full Bayesian inference, and here I show the full posterior distribution using this corner plot. However, in this talk, I will focus on the constraints on the warm dark matter mass and the species fraction with respect to the cold dark matter particles. Here, the warm dark matter mass is given in the x-axis and the uh, species fraction is given in the y-axis. I showed the 95% credible regions here. The dashed and dashed dotted lines show the current best constraints on these mixed dark matter scenarios. We see here that the constraints will be improved with future SK observation. As expected, the constraints will be most significant when sources in the small mass halos impact the intergalactic gas. Here, here they correspond to the DPL and the floor model. And to give you and to quantify this improvement for the floor and DPL model, the constraints will be improved by 4 times with 1,000-hour observations with SK. In a similar manner, we also studied mixed dark matter scenarios where the dark matter particles were fuzzy instead of warm. We found similar constraints as before, um, where we assumed a warm plus cold dark matter scenario. In summary, our study found that the epoch of reionization observations are a new window onto understanding the nature of dark matter. This is because the differences in dark matter models are more distinct at these earlier times where cosmic reionization occurred. The most significant impact of the dark matter models is on the timing of the reionization process. The non-cold dark matter models will delay the cosmic reionization process compared to the cold dark matter scenario. We have also found that the constraints on the dark matter models will significantly improve with upcoming observations of this era. In the future, we also plan to simultaneously analyze both these observations of galaxies and the 21 centimeter signal, which are complementary in nature, and we expect the constraints to improve when we simultaneously use both these type of observations. With this, I conclude my talk. Thank you.